Okay, so this is the second set of videos from chapter 14 on heat as energy transfer. So in this one we're going to look at a couple examples involving latent heat. So the first one is example 14.7 and it talks about making ice. So I thought that was pretty applicable, especially in terms of the NOVA film that we watched. So how much energy does a freezer have to remove from a certain amount of ice to make that ice achieve a certain temperature? Okay, so here's the amount of water we're talking about. Here's the temperature it's at currently, and here's the goal that we want it to go to. So we want to make ice because, of course, if it's below zero, it's going to be ice for water at least. Not necessarily for another substance, but so that's going to be ice, and we want it to be negative 12 degree ice. All right. So the question is, how much energy is it going to take? How much energy are we going to need to do that? So I think we need to kind of think of this in three parts. So I have it labeled energy 1, energy 2, and energy 3. All right. So energy 1, what I mean by that is the amount of energy that you need to reduce the water from 20 to 0. And that's not including like the phase change. Okay, so that's just what we did in the last section where we go mass times specific heat times change in temperature. So we want the mass times its specific heat times 20 minus 0. Okay, so the mass was 1.5 kilograms. Specific heat that we were talking about, if you remember, I guess I could pull up that table, but I'm not going to. It was 4186. And then that's going to be times 20. The second phase is what you need to actually make it change phase, I should say. So the second part of the energy is going to come from that change from liquid to solid, which is the latent heat of fusion. So that's why it's called L sub F. So we've still got 1.5. And then for that thing to go, for that water to go to change state to ice, we got to use L sub F for water. Get rid of my cat. Hold on. Oh. And for water, let's see, what do we have? So we go look at table 14.3, and we have 3.33 times 10 to the fifth joules per kilogram. Remember to convert that, okay? So you got to make sure you convert those figures in the table. And then we say the third part of the energy is going to come from once it's actually solid ice. We don't want just like negative 1 degree ice. We want negative 12 degree ice. So we've got to do what we had before. And that's just what we did in the previous section. So we're going to go, okay, once again, 1.5. That mass hasn't changed, of course. Mass is conserved, haha. And for ice, what's the specific heat for ice? We need to go look that up in the table. So let me scoot this over. I think I have that right here. Let me get it in there. So let's see. Water, if it's ice, the specific heat is 2100, if you can see that. Okay. Scoot this back over. Alrighty. So we're going to put 2100 in there. So notice it has a different specific heat when it's a different phase. And minus a negative is 12, so then we just put that in the good old calculator and we'll have what we need. So if you do significant figures, the book says that that's 6.6 times 10 to the fifth. I'll just trust it on this one. Joules, which you'll notice a lot of the time in this section that's being converted to kilojoules, so we'll say that's 660 kilojoules. Okay, so that's how much energy it takes to accomplish that. It's a decent amount of energy. So freezers use a lot of power. That's because I should say they use a lot of energy. Man, that's a physics misnomer. Okay, let's look at the next one. So the next one's pretty neat too. I think it says at a reception, you have a 0.5 kilogram ice cube, and it's placed in 3 kilograms of tea. Once again, we're going to treat that tea as water. It's pretty much going to have the same properties as water, just a tiny bit of tea leaves in there. So anyway, and that tea starts out at 20 degrees. So the question is, what is the phase of this combination? That's the new part that we have to worry about, because it could like perhaps the tea gets so cold that as a result it freezes solid. So is it going to be liquid, solid, gas, and also exactly what temperature is it going to have? So first I just said, or the book just said, consider 3 scenarios. It said, okay, consider scenario 1. To bring the 3 kilograms of water at 20 degrees down to 0, how much energy would that require? Well, it would require this much energy from what we've learned. Q equals mc delta T. So you plug those things in. Let's see. So we've got the mass of water. We said we were going to go 3 kilograms. Specific heat of water was, once again, that number we're going to memorize probably, 4186 when it's in its liquid form, times 20. And I'm just going to write that in kilojoules. So that's 250 times 10 to the third joules, or kilojoules. Okay, the second scenario we want to consider is how much energy would it take to raise the ice from -10 to 0. So maybe it would go the other way. So from -10 to 0, this is what would happen for that. So the mass of the ice was 0.5. Specific heat of ice we just saw a second ago is different. When water's in that solid form, its specific heat is different. So we get this instead. Also put that one in kilojoules. So 10.5 times 10 to the third, or kilojoules. Okay. That's not nearly as much in that situation. And then also we'd want to think, okay, how much energy would it require to like cross that boundary from solid to liquid, or from liquid to solid? How much energy would that take? Well, that would just be the energy due to the latent heat of fusion for water, or excuse me, for ice. So that'd just be that 0.5 times that figure. So let's just use 333 this time because we're working in kilojoules. So if you write your units, that's 0.5 kilograms. This is kilojoule per kilogram, so the kilograms are going to cancel, and you'll get 167 kilojoules. That way we have things that are all kind of the same units. So if you think about that, this is how much it's going to take that ice cube to cross the threshold if you're like going up in temperature from solid to liquid states over here that are kind of liquidy. Okay, so let me get rid of another cat. So if you think about it, 167 plus 10.5, that's still not going to give you 250. So it's just not enough energy for that ice to bring down the water. So we can pretty much think that hence there is not enough energy to cool the tea down to 0 degrees Celsius, and hence the mixture isn't going to be solid, it's going to be liquid. So we've answered part of the question right there. So the question is, what temperature is that liquid going to have now? So here's how we're going to figure that out, this blue stuff that I have down at the bottom. So what we're going to do is think about all the different things that are involved. So first, this 10.5, what was that again? That came from right here, right? So 10.5 was the amount of energy. Well, I guess I should put the main idea here, of course. Remember, energy is conserved. So in this case, we've got heat gain. So I put those all on the left. Heat gained. That's going to be the heat gained by the ice, right? And then over here, we've got the heat that's going to be lost when that liquid cools down because the ice is put in it. So since energy is conserved, we have that. That's where this whole equation came from. So that 10.5, that was the heat to raise the ice from -10 to 0 degrees, right? That's to get it kind of at the threshold. The 167 was the amount that you needed to get over the threshold. And then remember, we were imagining that we're going to have a liquid at some temperature, some unknown temperature T. So then we've got basically what we had in the previous section, where that's the heat to raise that water from 0 degrees. So now it's water because it's gotten over the threshold right here. And to raise it to that temperature T, which we don't know what it is. Maybe it's 10 degrees, maybe it's got to be less than 20, right? Maybe it's 3 degrees, I don't know. Okay, so then on the other side we have the heat lost by the T water stuff. So over there we've got the water. This is cooling, right? So you've got starting at 20, cooling a certain amount to that same T value so that they meet up. So if you imagine like the temperature spectrum here, I guess you've got the ice down here at -10 degrees. Here's 0. Here's 20 degrees. So this 10.5 gets you from there to there. The 167 gets you over this boundary right here at 0. And then you're going up a little bit more to some temperature T. I don't know where it's at. That's the value we're searching for, this T. So then on the other side we have the mixture of tea or water coming down to meet that same value. Okay? So that's where this equation came from. Then you're just solving for T. I'm going to say that you could probably do that. Should I fill in the step for you? I don't think so, but I guess we could solve a little bit. So let's see. So we've got 10.5 plus 167. So that's going to be what? 177.5 plus 0.5 times 4186. That's 2093D equals 3 times 4186 times 20. So over here we've got equals 12,000. I'm just going to do significant figures, 500. So really, I guess this is a 0 then. And this we'll just say is 0 for doing significant figures. And then minus, oops, made a mistake. So when we do 3 times that 4,000 times that 20, you get 251. And then we'll just say the rest are zeros for significant figures. And then when you do that times -T, you get minus 12,500T. Then you have one of those nice algebra 1 equations that hopefully we can all solve for T, or I don't know what to tell you. So anyway, the mixture, it turns out, is going to be at 5 degrees Celsius, which kind of matches the little diagram there. Okay, one last question. Let's look at this one. This one's probably a little bit, well, I don't know. I think these are all pretty interesting, but maybe that's just because I haven't studied heat before, and this is fun for me. Okay, so determining a latent heat in 14.9. It says the specific heat of liquid mercury. So they gave us the specific heat of liquid mercury. They said, okay, take 1 gram of that, put it in a calorimeter with a certain amount of water. So the calorimeter in the water is already at 20 degrees Celsius. And the mercury is going to start out at -39 degrees. So mercury, pretty much whenever you encounter it, is in liquid form. So that's the only point where it's solid, is if it's below -39 degrees. If you're having trouble, I mean, you can compare it to water, but if you also remember, think back to the Nova film where they had like solid nitrogen and solid oxygen. Remember, those happened at like super, super low temperatures for those substances. So mercury is kind of like one of those. It happens at a low temperature where it's solid. I mean, water's solid below 0, but mercury is solid at even lower temperature, -39 or below. Anyway, so that's the melting point of mercury. So the question is, what we want to find is, what's the latent heat of fusion for mercury to cross that threshold from solid and then melt into a liquid form. That's the idea. So once again, of course, we're just going to apply a conservation of energy and say heat lost equals heat gained. So the heat that's lost is going to be by the water in the calorimeter. So when we put this cold mercury in there, there's going to be heat lost. The heat that's gained is going to be the heat gained by the mercury. So when this mercury is submerged, well, I guess not submerged, but mercury. When the mercury is put into the calorimeter, the water and the actual, contact surfaces of this one, we'll say this one's made out of aluminum. So we'll say the calorimeter is aluminum. When that happens, the mercury is going to gain heat. I don't know how much, but we'll just have to see what happens. So we've got the heat that's lost by the water, the heat that's lost by the aluminum calorimeter, and the heat that's gained from the mercury. That's going to happen in two parts, right? Like we've seen in these problems. There's going to be that threshold value where the mercury melts, and then whatever amount of energy it takes, whatever amount of heat it takes to um, for the mercury to raise up to a certain temperature. So let's plug the values in and see what happens in this one. Okay, so heat lost by the water, how much is that going to be? So we're going to say the water goes from 20 to the final value. So we measured in this system, we did an experiment to do this in a lab, and we found that after you actually put the mercury in the calorimeter, the system reaches 16.5 degrees. So the water is going to go from 20 to 16.5. So we're going to say that's going to be the mass of the water. So what is the mass of the water? 0.5. I'm going to scoot over actually a little bit more. So let's scoot over here. So 0.5 for the mass of the water. Specific heat of the water was 41. Whoa, getting sloppy. 86, just like normal. And we said it's going to go from starting at 20. It's going to end up at 16.5, just like all of the system. Okay, so then the aluminum calorimeter container, what's it going to do? We said it's going to be, oh, oops, it's not 0.5 for the water. We said the water was 1.2. So the calorimeter container is 0.5 kilograms. Since it's aluminum, do we have that value from before? I think aluminum, if you look it up in the chart, is 900. Am I wrong? Yes, I see it in the book. 900 for specific heat of aluminum. And then it's also going from 20 down to 16.5. Okay, that's on the heat lost side. Whew, hope we can fit this in. On the heat gain side, remember we have the threshold and then the heating up after it's past that threshold. So the threshold is just going to be the mass times the latent heat of fusion for mercury. Mercury's atomic symbol is Hg, so this is mass Hg times LHG, and that's what we're looking for, right? We're looking for LHG. So we've got that plus the heat to heat it up. So what's that going to be? That's just going to be mass. So we had 1 kilogram of mercury. Specific heat of mercury, oh, they gave us that. It was 140. And the temperature difference is going to be, what was it? 16.5 minus negative 39.5, right? No, just 39. Okay, so you have to be real careful on that. So on this one, the difference between the original, remember it's like an absolute value, so the difference between the original temperature of the water and the calorimeter was between 20 and 16.5. So this value right in here is going to come out to like 3.5, and so is this. That's the difference from the beginning to the end. The difference from the beginning to the end for the mercury is a lot more, right? It's going to come up all the way past 0 from negative 39, so it's like the absolute value. It's the distance between those two temperature values, if you want to think about it. I like to think about it as a distance. So absolute value is distance, right? Anyway, so you plug all those numbers in, and this is all just one great big number. It turns out to about 19,000 joules. Then you say, hey, the mass was 1 for the mercury, so I can just put 1 in there times the thing we're looking for. This is all just one number. It's about 7,700 joules. So the latent heat of fusion to get mercury to go from solid to liquid, how much energy does that take? Well, it takes 19,200 minus 7,770 all over 1. So what is that? Several thousand. about 11,400 joules per kilogram. So the way that that's expressed in the table is about 11 or 11.4 kilojoules per kilogram. That's the way it's in the table. So that's the value for the latent heat to get mercury to change from solid to liquid or from liquid to solid. To accomplish that transformation, that's how much energy it takes. Okay? Hope you found this video useful. Good night.